Buongiorno a tutti, grazie all'Ingegner Molfese innanzitutto di essere presente, e dato che siamo già in ritardo partirei subito, Lucano, se sei d'accordo.
Perfetto, la registrazione è partita.
Buonasera a tutti, sono Paolo Ravazzani, sono il direttore dell'Istituto di Elettronica e di Ingegneria dell'Informazione e delle Telecomunicazioni del Consiglio Nazionale delle Ricerche, e anche stasera siamo qui per i giovedì dell'Istituto, i giovedì di EIT. Abbiamo l'onore di avere stasera un intervento da parte dell'Ingegner Molfese, nel ricordare, come faccio sempre, che essendo l'evento registrato e poi caricato sulla nostra piattaforma YouTube, è fatto obbligo di informare tutti i partecipanti di questo aspetto e del fatto che poi verrà pubblicata la registrazione. Mi fermo, ringrazio ancora l'Ingegner Molfese, passo la parola a Lucano Strambini che farà da nostro ospite.
Perfetto.
Verso l'Ingegner Molfese.
Perfetto, sì. Grazie mille Paolo. E switchiamo in inglese perché ci sono alcuni ospiti in inglese, quindi magari così diamo la possibilità a tutti di seguire meglio la riunione.
Assolutamente sì.
Perfetto, ok, ottimo. Okay, so thank you to everyone, and thank you very much to Antonio to be here. And a few words about Antonio, and then I leave him the floor. Antonio is currently holds the position of General Manager in the Smart Power Technology R&D division of STMicroelectronics. And in his current role, Antonio is responsible for guiding the strategic direction of R&D projects, ensuring that STMicroelectronics remains at the forefront of semiconductor industry. His efforts are focused on maintaining the company's competitive edge through continuous innovation and development of new technologies. I have the pleasure to know him during his PhD period. We have the same period of PhD, and it's a very pleasure to us to have Antonio here with his talk and presentation. So I leave to you the floor, and thank you very much again, Antonio.
Thanks, Lucanos, for the very nice words. For me, it's a pleasure too to be here, to be back, let's say, in this environment of my university. Basically, I know many people, let's say, inside the CNR. And let's start with my presentation. So today, I want to talk about my work in STMicroelectronics. So basically, I will talk about the innovation in smart power technology and what we do in smart power technology R&D at STMicroelectronics. So first of all, I would like to start telling you who is STMicroelectronics. Many of you know this company, but maybe some other don't know exactly all the things that STMicroelectronics is doing. So I will talk a little bit about the concept of innovation that is very important for us. Then I will go into the details of smart power technology BCD and about the application and the future trends of this kind of technology. So let's start from telling you who we are. So STMicroelectronics is a company where we create and we make technology. It's one of the world's largest semiconductor company. There are 50,000 employees, and almost 20% of the people are involved in R&D. Last year we did 70 billion revenue. And we have many manufacturing sites because we are a company that also makes the wafer. We are not a fabless like some of their competitors. And let's say we are present in many locations in the world. Basically, as you can see, we have a research and development center almost everywhere. Most of the center are in Europe because STMicroelectronics is a European company. But as you can see, we are also in the US and also in Far East. What are our strategy? Basically, there are three long-term enablers. The first one is to sustain the smart mobility. So STMicroelectronics is very involved in automotive markets. So what we do with our products is to help manufacturers to do better, let's say, cars, so safer, greener, more connected. We are also involved a lot in power and energy. Basically work in the industrial domain, but also in the consumer for power and energy, in order to increase the energy efficiency. And of course, we are involved in what is called the cloud-connected autonomous things. So on the proliferation of electronic devices that are connected between each other and also enabled by AI. So in order to do these three main pillars of our strategy, we are based on our internal technology, basically. So when you look to what ST is working on in terms of technology, you find a very large variety. We go from MEMS, so microelectronic mechanical system for sensor and actuator. We have some part where we're still working in advanced CMOS, even if, as I will show you, we are not working in a very advanced node like 3 nanometer and 5 nanometer FinFET. We have a large part of technology that is, but we use FinFET through Foundry in this case. We are involved in analog and RF CMOS. We have a large section that is working on the development and also the production on embedded non-volatile memory. And as I was saying before, we work on smart power technology. So it is the topic of today, is what I work on, so on BCD technology. We have also activity on discrete, so power MOSFET, IGBT, silicon carbide, gallium nitride. I will talk a bit later also on this topic. We have some technology that is vertical intelligent power that's still very linked to smart power and discrete, and also we are working in optical sensing solution. Internally, we have also technology for packaging. That is another important field above all in the last period. So today, as I said, we will concentrate more in smart power, and I will tell you something also about discrete because it's something quite close to my activity. So basically, we are driver of innovation. As I told you, we have almost 10,000 people working R&D, and each year ST is spending about the 12% of the revenue in R&D. So this is an important part, as you know, for semiconductor. It's very important, the investment in R&D, but one can have a question, why we do R&D? We do R&D because, as you know, we are working in an innovation environment. So for us, it's really key do R&D in order to enable innovation. Okay. So, and basically, what does it mean innovation for us? So on this, I would like to spend some word basically on the meaning of innovation. So when we talk about research, today I am talking to inside a community of researchers. Research is the transformation of investment in knowledge. So basically you put money and build a knowledge. And this is very important because this is the basis for the innovation. Why this is the basis for the innovation? Because the innovation is exactly the transformation of this knowledge built through the R&D, through the research, into money, so in our profits. So basically, the innovation is the process of bringing the new idea, methods, product, service, and in order to have a significant and positive impact that is, for a company, this means the possibility to gain a profit. And so how the innovation boost the company profit? Basically, in three ways. Normally, for a company like us, doing innovation can have three possible meanings. So the first one is that we introduce a new product, completely new, something that is not existing yet in the market. So this is with very added value. This is our key. And in this case, what is very important is to be fast, because we need to introduce this new product before our competitor, let's say. The other important point that for which is important innovation is that the innovation can bring the creation of new process that enable cheaper product. So we are not doing a new product, completely new, but we are doing something better. So with smaller, with less process step and so on. So also this point is very important, because we have many applications that are here since many years, but also in this there is a lot of innovation, because we need to shrink the dimension, to reduce the cost and so on, in order to be profitable. And then the last one, the other very important point, is to create better product. So we have more or less the same application, but we increase some performance. And also in this part, it's very important, for example, the analog part and also the power part. Okay, so this is the 3 points that drives our innovation and the way where we want to go in order to obtain a profit. If we look to the semiconductor industry, basically, if we look to what is the most important part of the most famous part, not the most important, the most famous part of the semiconductor industry, we talk about as you know, about the Gordon-Moore. No? So you are expecting that almost each 2 years, there is the number of transistors that you can obtain in an area is doubling. This law, it was formulated 50 years ago. Everybody knows very well, and it was possible to follow this law till now, basically. So, and today we have, for example, this is an example of some years ago. We have in a processor inside a mobile phone, something like 4 billion transistors, and we are going above 10 billion in the last period. And we had to change the architecture of the device in order to reach this performance. In this case, as you can see, the roadmap of the development was really clear. We know that it was necessary to increase the number of transistors inside the area to improve the performance, to do smaller device, to do more cost effective. And let's say for this kind of application, in the last year, we have seen that only few companies were able to reach the most advanced node. Why? Because at the end, it was necessary from technology point of view, increase a lot of the cost. There was an evolution in terms of lithography. It was needed to introduce new material. The costs were so high that, let's say, it was impossible for a small company to sustain it. And so you can see that recently, most of these applications are covered by a big foundry like TSMC, that can have the volume of many other companies. Okay, here the electronic system miniaturization was driven mainly from the processor power capability and the storage capability, so the memory. So from one side we have the Moore's for let's say the transistor. On the other side we have the capacity to increase the number of bits at 4 millimeters square for the memory. Okay. But this is only a part of the semiconductor industry, and is the part that we can call more Moore. What I work on is something a little bit different. So is what we call more than Moore domain. In the more than Moore domain, as you can understand, there is no roadmap. So the roadmap, or at least the roadmap is not so easy to be defined. Basically, in the Moore law, you can see that the objective was really linear. In the case of the more than Moore domain, what is driven the roadmap is the evolution of the real application needs. So the innovation in this case is not to bring more transistors, for example, in a determinate area, but the application is looking for a new product, the new product is looking for the technology, the right technology to address that kind of product. And there is another important aspect for the more than Moore domain. Basically, we can reuse some of manufacturing assets that are not more useful for the most advanced node, but or for the most advanced processor, but can be very useful in the more than Moore domain. So, if we go to look how can be in some way described the more than Moore domain, you can see that you still have an evolution in terms of technology node. The technology node, as you know, is indicating how many transistors in the digital part you can integrate inside your chip. So there is still the evolution in terms of more Moore, so miniaturization of the logic part, miniaturization of memory, increase of the processing. But on the other side, there is what is called the more than Moore diversification, where you start to have other blocks like ref, passive, high voltage power, the sensor, you can have biochips, silicon photonics. So, and you can, in this plane, you can move using solutions that are system on a chip, so solution where you put together advanced technology node and some other of these blocks in order to do your product. Or you can also have a situation where you have a system in a package, so you put together some of these technology nodes, not in the same chip, but putting together different chips. And with this kind of approach, you can really target different application from smart industry, smart home, smart things, Internet of Things, smart driving. So in this kind of domain is where we find BCD. And BCD was a concept that was introduced many years ago in the 1985. This is the picture of the first product realized in a BCD technology. And this BCD, what does it mean? BCD, it means bipolar, CMOS, and DMOS. So in this technology in 1985, it was put together on the same chip, on the same wafer, three kinds of technology. So the digital part, that is the one driven from the Moore law. The analog part, that is, let's say, at that time was figured as the bipolar. Today we do analog also for CMOS with CMOS, but let's say in that time was the bipolar, and the power part. So a part where it's possible to drive large current, large power, or high voltage. So in 1985, ST introduced this concept, and it was present and merged in one planar process platform called BCD. Since that time, we sold more than 40 billion BCD devices. For this invention, ST has been recognized as with the IEEE milestone. That is a very important award for invention. Is recognized. If you look to the list of the people that of the company that has been awarded with IEEE milestone, it's impressive. It's very an honor to be part of this history. So if we look to the evolution of BCD over the year, you can see that since the first product realized in BCD in 1985, this BCD was working with a 4-micron technology node, so very old technology node. Since then, we had anyway an evolution in terms of technology node. Today, for example, we have a technology that is a 40 nanometer technology. Okay, it's not a 3 nanometer FinFET, but it's still with a large increase in terms of logic density. And during this year, there was an evolution in our roadmap, and as you can see, with different with basically 3 different directions. So at the end, we had the direction that was still following with some delay the miniaturization of the logic part. So, and we reached the BCD40, and normally we call this part of our roadmap high density. There is a part that is more looking to the performance of the power to increase the capacity to integrate power. We call it high power. And there is another branch that was moving that we call high voltage, where we went to address high voltage application. But just to describe in a better way how a BCD product look, let's go to take an example. So this is a chip realized in BCD product. It is one of the many that it has been realized during the year. As you can see, you can easily identify 3 regions. So there is a region that is the part that is digital, so that is using CMOS for signal processing. And in this example is around 1/3 of the chip, but depending on the partitioning, you will use different technology. So in this part is 1/3. There is an important part that is analog, and it is all the analog blocks are used to interface the external world, and also to interface the digital part with respect to the external world and the high voltage and power part. Because there is the third part that is, as I was saying, the high voltage and power part. Here in this section, we have a high voltage device or power device in order to drive external load. So in this case, we have a solution that is integrated that can cover different applications. Different applications that can go from automotive. I was talking before about smart mobility, industrial, personal electronic, computer, peripheral. There are many applications for this. And when we look to a BCD product, of course, in this example, it's quite simple. But when, for example, we look to the digital part, you can also find the digital part some advanced development also in terms of non-volatile memory. For example, recently we introduced in the BCD technology the phase change memory, that is an emerging non-volatile memory that is used today also in the most advanced technology node for microcontroller. And today we integrate this memory inside a BCD. This is an example of a product that is working as our wireless charging inside a mobile phone. And as also in this in this complex product, you can see the digital part, you can see a memory, that is the phase change memory, still the analog part, and still you have the power section. So regarding the power section, why the power section is so important and why we work on optimize the power section. One of the most important efforts that my team is doing is try to improve as much as possible the performance of the power section. This is important because basically we can integrate as much as possible power in less space, in a smaller space. For example, imagine that you are able to save only 1 watt per hour for each phone that you have, for each phone recharge cycle, and multiply it for 1 billion of units of mobile phone everywhere. You can understand that is a very important value that you can reach. So basically, optimize the power part. So to be able to reduce the power consumption is very important in terms of portability. So in order to reduce reduce the recharge time, for example, or to increase the battery duration, you can reduce the size, and of course this is important also for in terms of cost, if you are able to do it smaller and then to have a lower cost. So, and how we worked on the power device evolution? So basically, the power device since the beginning is something that looks like more or less MOS, but with some specific feature. No? So in this example, there are a cross-section that is give an example of a power device. Basically, you have a source region, the body that is connecting the body. This is the body region, okay? So, and then there is a drain region where you can recognize, for example, this polygate that is going also on top of a region where there is a thicker oxide. We call it the fill plate, okay? Basically, when we did the first power many years ago, we had some performance. In this graph, I put the performance of a 40-volt device during the different technology that we developed in the last year. I started from BCD3 in this example, and by normalizing let's say, the performance of the BCD3 in terms of radiation by area, so specific radiation. So if you want to reach, for example, a 10 milliohm resistance in the on state for this device, in BCD3-6 you add the dimension 1. Okay, so in each generation of our BCD, we were able to reduce the area occupied to obtain the same performance, as you can see. And this was not driven by the new technology node. It was driven by the improvement in the architecture. For example, we changed the architecture of the body, we changed the architecture of the drain, we changed the fill plate architecture. So also in this kind of technology, we have an improvement during the years, but it's not driven simply by the miniaturization of the technology node, but is driven by the change in architecture. And this is not the only one factor of merit of a smart power technology, because we talked about RDSON, that means the power part. But then you understand that there is the analog part that is also important. And there is also another important part, the isolation, because when you drive high current and you have high voltage, you need to find also a solution to have good isolation. In this example, we introduced a concept, for example, in the BCD, the deep trench isolation, that are trenched vertical, that are able to separate different regions inside the chip to reduce the parasitic. And also, very important is also how you have what you have in terms of metallization. For example, in a BCD technology, you always need to have a very thick copper as a last metal, because it's needed to drive and to manage high current. And going back to the deep trench isolation module, here I want to explain what is the meaning of improving the immunity to the latch-up, for example. If you look, if you have two different N-type well and you put in the middle, let's say, the deep trench isolation, you are able to suppress completely the parasitic bipolar between the two and well. In this example, this is the gain of the alpha of the lateral NPN bipolar. And if you don't put the deep trench isolation, and we call it, for example, junction isolation, you will see this value as a function of the distance between the two and well. But if you put a deep trench isolation, as you can see, the gain is decades lower. Okay. And on top of this, so if you want to isolate different wells, thanks to DTI, you can reduce also the area, because you are able to pack together more region of your chip, thanks to the fact that they are well isolated by the deep trench. So this is another typical feature of our BCD technology. In general, what I want to underline you are also in general the parasitic components that are important in this technology, and you have to take care of them. And in order to take care of them, you can use different isolation scheme. As I can tell you, we can use the standard isolation, junction isolation. we can use the deep trench isolation. In some technology, we used also a substrate on isolator technology. So you have your dioxide even inside the silicon. And regarding metallization, as I was telling, the metallization are important to drive current, but also the finishing of the metallization are important because they are enabling different package. Okay, so where do we use the BCD? Mainly, as I was saying before, there is the automotive market. In the automotive market, as you can see, there are plenty of chip inside of electronic components inside a car, and in many of them, it is needed a BCD technology. I'll give you an example. For example, in order to reduce the CO2 emission, there was in each of our BCD was used in automotive in order to have, for example, direct injection driver for different also regulation from European. So as you can see, you can really see the evolution of the full injector that has been also driven by the evolution of the BCD. But of course, today, maybe it's not sufficient to have to work on the internal combustion engine. So most likely, the most recent BCD will not be there. But anyway, there is still need of BCD. If we look, for example, to battery management system, so in a car, an electric vehicle today, there are battery lithium-ion technology with the lithium-ion technology. And in order to maximize the capacity of this kind of battery, it is needed to have a battery management system. And the battery management system is a system that is able to measure the capacity of each cell that is composing the ion lithium battery. And so in order to increase, to keep high the efficiency, in order to monitor the safety, because we need to avoid the thermal runaway. In general, also, you need to communicate the data that you obtain on the metering of the battery in order to store them and also to check them, basically. So we have basically product using BCD that are able to measure the key parameter of the battery, to control the energy, to verify that there are not cells that are weaker, and in order to, it's very important to balance the performance of the different cell components of battery, and also to verify which is the status of the charge and the status of the health. So BCD was using for the motor, today is using also for the battery management system. Other application for BCD, we go, for example, in the energy management. We know that from the production of the electricity up to what we use, for example, inside a processor, inside one of your laptop, you can see that at the beginning you have, for example, 220 watt, then there is, of course, the thermal loss where we produce the energy. In each phase of the transmission, so AC transmission, power distribution, DC to DC conversion, DC conversion inside your laptop, in each of these steps you lose energy. So from the initial part of 20 watt, as you can see, we obtain 60. So that's very important to reduce the consumption in each of the conversion that you have. BCD is very important in all of this part. The performance in terms of RON are very important, but as you can imagine, it can be even not enough. And in this field, it's very important also the optimization, not of BCD technology that is able to do the power, the CMOS, and also the analog, but you need to have some specific components, for example, low voltage MOSFET, IGBT, recently gallium nitride HEMT, silicon carbide MOSFET, in order to have a very, very good performance in terms of RTSON, for example, in order to reduce the losses. As you can see here, silicon carbide and gallium nitride are new material. We are not talking anymore in this case about silicon, but they are very, very important because they give the possibility to work at very high voltage. The performance of silicon carbide and gallium nitride are very good. At high frequency because thanks to the larger electron velocity, and also above all for silicon carbide, they have very good thermal conductivity and melting points. So, for example, silicon carbide today is widely used in automotive thanks to the properties at high temperature. While GaN is for sure good for high voltage, but above all when we will need to have high frequency. So, but if you have a discrete MOS, so in this case we are not talking anymore about a BCD, but a discrete MOS, you still need a BCD in order to drive the gate of this discrete MOS. And also in this case, the chip, the ASIC that is able to drive the gate, for example, of a discrete is still a BCD. And for example, to drive the gate of an IGBT or a silicon carbide or a gallium nitride, we use BCD. And if you go at very high voltage, because in some application you need to go at 600 volt, 102 kilovolt, you need also the ability to be isolated, well isolated. The reason is that there is a matter of severity in terms of circuit protection, people safety for battery system, people safety for grid connected. So you need something that is able to isolate with 2.5 kilowatt, 4 kilovolt, 6 kilovolt, 10 kilovolt. And we do this also in BCD with what we call the galvanic isolation. And also in galvanic isolation, that is basically an inductor or a capacitor that is realized directly on the back end of a BCD technology, and it is able to sustain 6 kilovolt or 10 kilovolt if you put two in series. And this is our roadmap. And also here you can find some example. For example, if you look to a car where are widely used the silicon carbide IGBT, the gate driver of this silicon carbide IGBT are realized with a BCD with galvanic isolation. It's a technology proprietary from ST. We shipped already 100 million units because they are used in most famous car that we have today, electric car. And also not only in isolated gate driver for electrification, but also that are used, for example, this galvanic isolation BCD also in digital power controller where we need to have a reinforced galvanic isolation. So basically, the BCD is not working only for application at low voltage, but also for application up to 10 kilovolt isolation in this case. So, but in many of these examples, as you can see, we are not having only one die inside the product. As you can see here, there are 3 dies in this product, and we talk about a system in a package. And indeed, this is the new evolution of also of smart power, because today we can have a very good BCD, but maybe we need to put together a gallium discrete device, and you can do this product at package level. And for packaging, a system in a package, you have a different configuration. You can have a die-to-package interconnection. You can put in the same package passive. So maybe you need to have a very large capacitor, and you integrate with our BCD inside the package, not inside the BCD, because it's more cost-effective to have inside the package. There are many applications where you put the chip side by side, as I described before, and also there are advanced packages where you put your different ASIC one on top of the other. And this will be another important trend in the future. Maybe we will keep our BCD with a less performance in the power, but we will put on top of it or on the side of it a gallium nitride or a silicon carbide device that has the right performance to reach the RDS-on that we want to obtain. Also, for this, I have an example. This is a digital motor control where you can combine together BCD, a technology CMOS, a power MOS, also a gallium nitride, all together inside the same chip, and you reach the optimized performance combining all these product together. And finally, if we talk about gallium nitride, we said this is a discrete device. The first application we are observing in the market are discrete, but is it possible to build something similar to BCD as we did in 1985 also with gallium nitride, for example? The answer is more or less yes. In fact, today what we are doing is putting together the gallium nitride power HEMT, other device with lower voltage. For example, we have the 100 volt, we put also the 12 volt. We put some passive components, so MIM capacitor of some circuit in film resistor. At the end, we are also building some technology platform in gallium nitride where you put together different devices, not only the discrete. So this is also another trend that we are following with smart power. And also in this case, what you see? You will see that in the future there will be, for example, still a BCD technology that is always needed because you need to drive in some way, and the logic part and the analog part that you can do a BCD, it will be still superior. But part of the driver that is driving the power stage will be inside directly in the technology that is realized in the monolithic gallium nitride technology. And you will put together these two ASIC inside a system package, system in a package. So basically, I give you a lot of examples, but just to summarize, what I've shown you is more or less what we do normally in our job. So basically, as I told you, we are doing a lot of innovation, but of course we need to work in the different field of the R&D. Okay, which are the different columns of the R&D in my vision? Okay, we have the fundamental research. Okay, that is the screen of new material and process. Basically, most of the activity in this column are done at the university research center, in my opinion. In a company, this part is less interesting because you really need to have to look to the basic of the material, which are the property of this material and so on. Then there is what we call the advanced semiconductor R&D. And it means that if you select a material, for example, suitable for doing a very good capacitor, then you arrive and you discuss with a company interested on this kind of dielectric, for example, and we try to integrate this material inside a process flow, so together with other stuff. And this is where, in my opinion, starts the work we are normally doing. Okay. Once we have proven that this component that is using, for example, this peculiar dielectric is working well, at this point we need to develop the technology, because develop the technology means that we need to qualify the technology, verify that is reliable. For example, put this device inside a PDK, so let a designer use this device, build a design platform, and at that point we have, let's say, a technology with a product that uses that material that was screened maybe in a university center, and then we need this product is working well in one part, but still we need to manufacture in billion or million of parts. So the other very important column of R&D is also the manufacturing. And in each of these, there is innovation. There is innovation in manufacturing, there is innovation in technology development, in advanced R&D, and of course, there is innovation in fundamental research. If you look to this chain, most of these, the three columns on the right are very often done in our company. I think that in the future, we will see more and more that the screen of new material it will be done more in academia and research center. So in conclusion, semiconductor industry changed our life with in the last years with all the products that we see each day. We have many emerging applications in automotive, energy saving, in personal electronics. All of these, as I told you, are using, for example, BCD technology. The silicon technology remains the reference. In my opinion, it will stay there. A BCD, as I told before, most likely will still be there even when you integrate the new material, but the use of new material is growing. And in general, let's say, as I was saying before, there is an important point that is the innovation, also the base research activity are, in my opinion, moving also to the university and the research center, because as we need to investigate new material that not usual for the industry, it's very important to have from research and center university the selection of this material and the study on the base properties of this new material. I think I completed. I don't know if it was too long or it was okay. Please.
Thank you very much, Antonio, for very nice presentation and talk, and very interesting information also from our side, in order to have an idea on what are the trend for the industry in terms of semiconductor, and more in this case in terms of smart power application and technology. And no, the time is good. It's good. Very much. Thank you for your time. So now we have a little bit time for some question, curiosity from the audience. And so if you have some question or other or some curiosity and comment, you can raise up your hands. And or if you have the possibility, you can write on the chat something, and you can write something on the chat. And so okay, we have a question from Giuseppe. You can open your microphone. Okay, yes, floor is yours.
Yeah, do you hear me fine?
Yes.
Yep.
Yes, this is Giuseppe Santillo from Synopsys. Thank you, Antonio, for your presentation. It was very informative and very good to understand where the industry is going. I had a curiosity about the evolution of BCD that you might see. You mentioned that BCD has shrunk to 40 nanometers nowadays. Do you see that going? Do you see BCD shrinking even further than 40 nanometers below that? Or is it going to be more a question of integrating, as you were saying, system in packages with more specialized dies, maybe for processing, you're going to be using other kind of technologies?
Frankly speaking, I think that the last node, well, BCD40 is the last normal node, let's say, with still a gate in polysilicon, let's say. So, in my opinion, BCD40 is BCD. For the next technology node, I think there will be some challenge. I think that if there is an increase of an increase of the system in package and also solution in package that allows to integrate together a BCD with an advanced technology node, most likely the next BCD will not be a system on chip, but a system on package, okay, with a very advanced CMOS and then a BCD in the range of 90 nanometer or 40 nanometer. The reason behind is that more and more will be difficult to integrate the power part with the digital part, because the new component are already at 28 nanometer, like the full depleted SOI or the FinFET in most advanced node, could be not compatible with the power, or in general it will be too much expensive to integrate it together in the same wafer. So I think that it's possible that BCD40 could be, the 40 nanometer could be the last, or the last BCD in terms of technology node. On the other side, sometimes the possibility to put together could have some, on the same chip, could have some advantage. So maybe there will be room for 28. We have some foundry that is putting in their roadmap up to 22, I guess, nanometer. But in their roadmap, they declare that they will do. We will see. Anyway.
Okay, thank you very much. Thank you very much, Giuseppe and Antonio, for your reply. And if there are some other questions, when we are waiting for eventually other question, I have some curiosity. And yeah, I understand that in order to have it's, as you say, it's difficult to have on the same chip power and logic with very small dimension. For example, as you know, as you mentioned, the FinFET or other kind of new architecture for transistor, CMOS or BJT. But I'm not have some lot of knowledge on the system on package approach, but what in terms of losses with respect to have system on chip, what is the difference? I mean, there are research in order to, it's possible, sorry, to improve the performance of the approach that is a system on package. I mean, the connection, loss of power and so on, or do you think that we have reached the maximum performance that we are able to reach with this kind of technology? I mean, the technology related to the integration of different parts on a package.
No, there is a lot of research on this field, and there are many solutions that are improving a lot the performance already. If you look to most advanced application, for example, in a processor today, you have the memory on top of the processor, and you have this stack that are very efficient. Also in power, there are technology without wire that are very promising. So I think that it will be really a challenge, an important challenge for the future to improve also on the package in order to have the possibility of decide where it is convenient to integrate in the same chip and where it is convenient to go at package level. But anyway, it's another very important part of the story of innovation. As I was showing, is what we call the advanced package. And in general is one of the most important trend that we see in the last year.
Okay. And do you think that the university, academia, and research center can give improvement and knowledge on this field, or is less an innovation part of the activity? I mean, is more innovation to improve performance, or is required, do you think, some other base knowledge to have a change in performance to improve in a very better way the performance of system on package structure? And so, I mean, do you think that we can give to industry a good contribution in terms of research on this field, or are only innovation part of? Do you think to have a better performance in
No,
this
I
time,
think
this
it will come also from the university, because of course when you go then at package level with solution that becomes more complicated, and for example the material completely different, I talked about galvanic insulation, for example, today.
Yeah.
If galvanic insulation, you need to sustain very high voltage inside the chip, but if you from this chip you take the wire, that high voltage that be sustained already on the package, and so in the package has material that are not typical from for the semiconductor. And this, for example, the study of the material, the property of a molding compound, how it react, is something really from the university. And so I think that from one side, I see that the company and the industry is working a lot on technology improvement, integrating as much as possible. It's very fast, but to study some specific item and to address some specific item with specific study and understand the root cause of some behavior is fundamental, the academia and the university, in my opinion. That's so. For this reason, I think that there is really a part of the study on the of the research that where the university can play an important role, and it's needed, the knowledge of the university.
Okay, thank you very much. And I think that we can have a lot of input from your side, and as new and research activity, or to drive the research activity on field that, for example, it's probably it's not known better because, for example, typically some areas move to some exotic material or some other kind of approach that probably in the future could be useful, but at the moment it's too far to the real application. So I think that some kind of input coming, for example, from collaboration activity could give a very, very interesting field of research for us, and useful results for the company in that field. That could also could be useful in a kind of competition with other countries, driven by the cheap problem that coming out some years ago. And so I think that also in some kind of political aspect that have to drive some to found some research field, research areas, it's better to have some input also coming from industry to drive properly also some kind of research activity in order to have the results that could be useful for everyone. So thank you very much, and
thank you.
For this kind of contribution, for this talk, and thank you very much for your time. And we don't have any other questions, so I want to thank again Antonio for his availability to contribute to this webinar series, and I wait you and to the next webinar that will be the next week. And so thank you again to everyone, and see you for next future collaboration.
Okay.
See you.
Bye. Thank you, everybody.
Bye.
Bye-bye.
Thank you very much to everyone. Bye.